Alrighty, 5.2 silicates. Let's start now. So, in this chapter, there are 2 pages of expected knowledge written. Firstly, write the formula of the anion in the silicate or aluminosilicate given its formula. I'll talk about that, both what they are. Identify SiO4 structure unit in diagram of silicate anions. Draw the repeating unit and write the formula of an extended silicate anion given its structural formula. This part is kind of similar to polymer or protein. So you are trying to single out a unit. State the charge on the silicate ion given its Si2O ratio. Write the formula of silicate mineral given the structural formula of the silicate anion and the metal ions present. State the charge of an aluminosilicate ion given its formula. Next, explain how cations hold on the surface of soil silicate are made available to plants. So a bit going back to soil chemistry there a bit. Describe the effect of acid rain in releasing cations from soil silicates. Again, environmental chem. Yeah. Explain the use of aluminium ions in flocculating clay particles suspended in water. Flocculation. Explain the use of silicates in water softeners. Getting rid of metal. Now, silicon. Now, let's just recap what it is and what do we know about it. It is in group 4. What group is that in? Metal? Non-metal? It is not really metal. It is not metal in non-metal as well. It is metalloid, isn't it? What does it mean again, if it's group 4?
It's non-reactive.
It's not really reactive, good. Yeah. It doesn't want to give away or gain electrons. It usually wants to share electrons. So what sort of bond would it want to make? Primary bond would be covalent. Wants to share electrons. Covalent. Yeah. So what do you expect? Would that be fairly strong, weak bond? Strong. Well, not probably as strong as metals, maybe metallic, but it depends on what it's bonding to. If it's bonded to something that don't want to give off electrons at all, then it's going to be fairly strong. Okay. Silicon itself, just background knowledge here. Second most abundant element, making up 28% of the Earth's crust. So Earth's crust is where we are standing on. Okay. So all the soil, rocks, other minerals. Okay. Usually they contain silicon as main component of it. Okay? Complex silicates are found in rocks, clays, and soils. Now, when you've got 8 in it, like sulfur and sulfate, nitrogen and nitrate, okay, you're talking about oxygen there. Okay, the most oxidized version of an element on atom is usually has 8 in it. Okay. So silicon and oxygen bonded to each other. And can consist of individual SiO4 tetrahedra or these linked chains, rings, sheets, or as 3D covalent network. So what makes up is this? So that's the smallest component usually when you look at any rock, soil, mineral. Basic unit for all silicates, which is SiO4. This structure is made stable by accepting electrons from other atoms. Well, again, it's sharing electrons, so covalent bonds are formed, and combination of those would make very complex structure like what you're seeing there. Okay? In silicates, oxygen atoms can be shared between 2 SiO4 tetrahedra. the charge on the silicate anion depends on the ratio of the SiO4. Now, if you want to highlight something, I would recommend you to highlight anionic unit there. Just circle or highlight there. Okay. What it tells you is that the silicate here, all the silicates here, have got different ratio of silicon and oxygen. For example, first one, SiO4, it's 1 to 4 ratio. And as a whole, there's a charge of 4 minus. Okay? Si2O7, so 2 to 7 ratio, and that's the smallest unit, it looks like that. 2 tetrahedra stacked with each other. And as a whole, you should have 6 charged. Okay? Now, we're talking about silicate, which is an anion here. What's your guess? What would it want to bond to? Good. Anions usually want to bond with something positive. What makes it positive underground? Well, usually metal ions, isn't it? Yeah. And metal ions, when we were talking about the mining part of it, a lot of metals are bonded to something, isn't it? Yeah, aren't they? So these are the partners of the metals, really. Okay. So if you pick up a rock, sand, grain of whatever mineral, okay, they would have one of these silicates, okay, as negatively charged part, and positively charged part would be metals, which often give colors to minerals too. Okay. So by looking at formula, the ratio of silicon and oxygen, you need to be able to work out the charge. Okay. Shall we try doing that? SiO4, Si2O4 maybe? Or SiO4 to start with. So if you have got SiO4, hopefully you're picturing that to start with. Okay? Now oxygen can make 2 bonds, can they? So you would imagine all these oxygens here have got charges. So what's the overall charge of this ion? I'm sorry, yeah. 4 minus. Yeah. It's basically that.
Is silicon always positive or
I wouldn't say positive, but because oxygen has higher electron negativity, it would be negative, isn't it?
So you could just have the like 4 take oxygen times by 2.
Mm-hmm. Would you like to try drawing Si2O7 then on your paper somewhere? So similar manner to this. Okay, silicon is going to be the center, and there are 2 of them. How do you make O7 around it? Remember, silicon wants to make 4 bonds. So each silicon would have 4 oxygens surrounding. Now 1, 2, 3, 4. So that's SiO4 unit. And this oxygen here, if you can picture that, that's going to be shared between 2 silicons, so that each silicon can have 4 bonds. Okay. Now counter charge.
-6. Because the oxygen in the middle doesn't have a charge.
That is true. 1, 2, 3, 4, 5, 6, 7. Yeah. 7 oxygen, and 6 minus, there you go. So you got the right number there too. So that's how we can find the charge on silicate ion. Okay. Okay, moving on. By the way, I've been doing this for a while, but when I put minus charges, I usually put circle. So that's not a bond. Yeah, that's different from bonds. I have to charge the charger. Okay. Now silicates. So as we kind of talked about before, they balance the charges with positively charged ions. You know what's present in the soil? It's the metal ions. Yeah. When transition metals are present, the mineral is usually colored. Now, as you've seen in flame color practical or AAS, atomic absorption spectroscopy, okay, in there you saw that metals usually give colors. So, now in the future, if you want to work with colors, if you don't want to work with anything that's like dull, like organic stuff, yellow, clear, or brown, work with minerals. They'll be colorful. Aluminium can also replace some of the silicon atoms, forming aluminosilicates. Now, this is another type of the building block of minerals. Okay, so silicates are building blocks, the smallest one. But when some of the silicons are replaced with aluminium, aluminium becomes part of the negatively charged ion. All right, and they are called aluminosilicates. Some examples. You don't need to remember these names, but also silicates, SiO4 as main block, and zircon, which has got Zr, which is zirconium, I think, is bonded to silicate. So that's what we drew just then, wasn't it? Sorosilicates, Si2O76 minus. So there's some minerals that's available there. You may recognize some of them. Emerald has got Si6, O18, 12 negative. Emerald. There you go. There's a formula for it. Be3, Cr3, Si6, O18. Now, again, what you need to be able to do with these slides, I'm just introducing what they look like, but what you need to be able to do, going back to student-intended learning, was that if you know the charges of silicate ion, you need to be able to balance the charge with the metal ions. Okay. So metal ions usually have fixed oxidation number, right? Sometimes you have to be given. Now chromium has got 3 different oxidation numbers, so you might have to be given. Yeah. But if you're given that, you need to be able to write the formula, or from the formula, you need to be able to find the oxidation number, vice versa. Yeah. It's really just adding and taking charges, and that's it. Okay. All right, moving on. Oh, in this case, by the way, beryllium is second group. It's in a group 2, so usually 2+, and it wouldn't usually change. So from that, you can look at the charge of chromium. Yeah, chromium ion. More silicate, and this one has got rhodonite here. I've never really heard of it or looked at it, but this mineral here has got interesting convention here. So it says manganese, iron, magnesium, and calcium, and 5 outside of it. What it means is that it could be any ratio mixture of those metals. Okay. But looking at this mineral itself, you see there are red spots, black spots, gray spots, white spots. Yeah. Usually the metals are the ones who give color. So you could get different ratio of them depending on spot of the mineral that you look at. Okay. Double chain, Si4O11 6 minus. Now you may be asked to draw this structure like what we did, or you could be given a structure and find this ionic formula for the ion. Okay, could be vice versa. Again, it's just a matter of counting. Okay. SI4 or 11 may be a bit hard to draw, but you've done SI2 or 7A. Yeah, similar, but it just becomes bigger. Okay. Start with silicons, that's the center, and put oxygen surrounding around each silicon, and then make sure they all have 4 bonds. Some of the oxygens would be shared. As long as you remember the rule, you should be able to draw. Yeah.
Would the silicons that go like 2 and then 2?
Yep. Yep.
Could it be in a long
Yeah.
as well?
Yep. No, you don't have this information, but you see the name there, double chain. So you would have double chain
So 2
of
rows
silicate.
or-
Yeah.
okay.
Yeah. So it would be, if it was a big rock, right, you would have one chain of SiO4, and then you would have SiO4 as a chain. And they are linked with some oxygen.
Right.
Yeah. So that repeating unit would be just SI4 or 11.
Yeah.
Yeah. Okay. All right. So if you count the oxygens which have got charges, that should be 6 minuses only. Talcum powder can be made from that. You can see the structure there, Mg3, Si4, O10. Now, you would also notice, you should probably take note of it, OH here can be part of the mineral. Okay? These guys do have 1 minus as its charge. Okay? So that adds to the complexity of the question. Okay? Mg3 plus, 3 lots of 2 pluses, yeah? And you should have Si4O10 is 4 minus. That's 4 minus here. Yeah? That doesn't balance out, does it? Because that was 6 plus 6, and then 4 minus. OH, you should know that they have got 1 minus each. There are 2 of them. So 6 plus 4 minus and 2 minus here. Okay? But at the end of the day, it's just an ionic compound, so you should be able to balance the charge. Okay? It just looks scary, that's all. All right, more silicates, sand, quartz, SiO2 is what you should usually expect from it. SiO2, silicon dioxide. You would have used that or seen it in the lab as well, even. Oh, that's, by the way, something that you would use in a quartz watch or silica when we do gas chromatography. There's a layer of silica in it. Yeah. So it's a powder of this. Yeah. So there's a lot of application to it. By the way, why is silicon considered as metalloid? What is metalloid more like?
Isn't it somewhere between non-metal and metal?
Good, yeah. So silicates need to have some of the metal properties as well as non-metal properties. When you look at quartz here, does it look like metal? No, it doesn't have the luster like normal metals have. But what is so special about this? Why is it used in quartz watch? What does it tell you? It's got batteries in it. What's it doing there?
Yeah.
Yeah. They're actually called semiconductors. They conduct electricity a bit. How it reacts to the electricity, that it starts vibrating. So a certain frequency, which is very useful if you want to make a watch, doesn't it? Yeah.
Is that kind of like sand having really high motion, like melting point sort of thing?
Hmm. Yes.
Is that like kind of like a metal property?
Yes.
So, yeah.
Oh, well, I would like to say that the melting point is due to the covalent bond.
Right.
Yeah. But I guess conductivity of electricity is the biggest thing for silicon property. And the silicon to be considered as metalloid. Yeah. All right, aluminosilicate. Now again, formula looks really long, but it's really just an ionic compound again. Okay. Mica, is one of the aluminosilicates, and that's where some of the silicon atoms are replaced with aluminium. That's it. Okay. So if you look at the formula there, what can you tell? You've got K what? KAl2. Oops. And then AlSi3O10. And then you've got OH groups, two lots of them. All right, by looking at this, what you need to be able to do is to find the charge of this aluminosilicate. -5. Ooh, that was quick. Potassium is just +1. There are 2 lots of +3, so that's +6 there, and 7 here. Yep. Do you remember? Yep. There are 2 lots of -2. That's the X.
-1.
Is it?
On
So this needs to be 0.
On the hydrox. 2 lots of -1.
He's talking about the OH. It's not negative 2, it's -1.
Oh, sorry. Yes, that's correct. Yeah. So if you solve this for X, it's really just addition and subtraction, isn't it? What do you get? Should be negative. But +6, +7, and take 2, so 5, -5, as you said before. Yeah. So that's all you have to do, really. Okay. You need to be able to just find this. Only difference with silicate is that aluminium is part of the complex. Yeah. Part of not complex. Complex is the whole thing. Aluminium is part of this silicate anion. Okay. All right. So ratio of Al, Si, and 2O is the same as the parent silicate. For example, talc. If you look at the silicate ion part, you notice the silicon used to be 4 and O10. If you replace one of the silicons with aluminium ion, you would get AlSi3O10, which is what you can see in mica. Okay? But the charge, of course, changes because you're adding something more positive to it. Aluminium substitute increases negative charge on the anion by 1 because of that. A few more examples. Whatever formula you are given, you just need to be able to do the same. Okay? You just need to be able to find the charge on aluminosilicate. And this is what we've been doing. Overall charge of silicate is always 0. It's just normal ionic compound. And charge on the anion of a silicate or aluminosilicate can be calculated by what we did. Use the charge of cations or use the oxidation numbers of Si, O, and Al, which would be, well, silicon would be 4+ always. Yeah. Oxygen 2- aluminium 3+. Yeah. What cations is usually given? Well, that depends. As long as it's not trunnion metals, you should be able to find that by looking at periodic table. Yeah. Following all right? So what is the formula of the anion in asbestos? It's got a bit weird number in there. I wonder why it's not subscript. So asbestos, if you inhale it, it's gonna start.
Cancer.
Yeah, it will start. Yeah, cancer. Yeah, because it stays in your lung. And anyway. So Ca2, MgFe, there are 5 of them, and Si4 or 11, there are 2 of them. So there are two ways of doing it. You could look at cations. Now, ion here may not be 2 plus, maybe 3 plus. You don't have the information for it. So I would look at silicate part of it only, Si4 or 11. How you can draw it? Hopefully you can draw that for silicons, and they all have oxygen around it. Count the oxygens and how many bonds which are not used up for bonding. Yeah. All right. In the diagram below, identify SiO4 structure unit and also identify the repeating unit. Have a go. So use the square brackets to draw them.
The first two the same.
SiO4 and
The
repeating
repeating unit.
unit is if you're given this, I would usually go the whole thing. I would consider them as chain. If you go back to, yeah, it is a bit confusing because you're not given the whole structure of it. Yeah, I think that's actually sheet structure.
So the whole thing is the repeating unit.
Whole thing. But if you look at Si2O5, when let's go back to there. When two silicons are sharing one oxygen, yeah, that needs to be considered as a part of it. I think that's how I understood. So the repeating unit in this case would be just, okay, if you start after the oxygen, you have to put the closing bracket after one oxygen too.
Do you have to include that bottom O that's bonding to the thing below as well?
1, 2, 3, 4, 5, 6, 7. Yeah, that was 7, wasn't it? In this case, yes. Oops, I was wrong. Si2O5. Si2O5. Okay. So that doesn't look like a very good diagram for it. I should have put something else then. Hang on, what I remember is it's ring structure for some reason. So if you start with after oxygen, you may have to put it there. Put the one. No, that will be the chain structure. Sorry, this is not a very good diagram for you to practice on. There are much clearer ones in the essentials and test. Sorry, we'll look at it later. But the same thing needs to be done as proteins or polymer. Make sure that you start at one point with square bracket and close with another square bracket. Other questions? What is the charge on a silicate anion which has a ratio of Si to O, which is 3 to 9? What is the formula of talc if silicate anion involved is Si2O5 2 minus? If two OH minuses are present and a cation involves involved is Mg2 plus. What is the charge of an aluminosilicate ion in phthalogopite, which is what's you are saying there? Alright, have a go at these three questions.